Good afternoon, and welcome to the session today. Did everybody watch the keynote this morning, Adam's keynote? Good. And how's your day going? Hopefully all good? Great. Well, we're very thankful that you're here, very excited for everyone to be here and spend this next hour with us. So we're going to be talking about how AWS IoT helps our customers build connected auto solutions easily and quickly with AWS IoT. My name is Ritu Kama. I lead the worldwide IoT go-to-market strategy here at AWS, and I'm transitioning into my new role as a principal PM on SageMaker Foundation team. You'll also be hearing in today's session from Michael Garcia and Henrik Stromberg. They'll do the intro when they come on the stage. So let's get into the agenda for today. To begin with, we'll be talking about what do we mean by connected auto? What does that mean? And then we'll talk about what tools and technologies AWS has to enable connected auto solutions for our customers. I'm sure you all caught the announcement of IoT Fleetwise. We'll talk a little bit about that too as well. And then we'll hear from Henrik, our customer from Wireless Car. He's going to talk about their journey with AWS IoT to enable connected auto solutions for their customers. And then we'll hopefully have some time set aside for Q&A at the end. Okay, so let's jump into it. We can all relate to this. Cars used to be all about mechanical systems, about electrical systems, and frankly, auto companies became very good at building cars over the course of time. But then when we think about cars today, they're not as much about mechanical and electrical system as it is about digital and the data that these cars are collecting. And customers expect digital solutions from their cars today. So by collecting all of this data, it creates a lot more possibility, and that's what we're here to talk about. And this is all driven by consumer demand. We can see this, that the customers are evolving and they're requiring and actually expecting more and more of this from the auto manufacturers. And the auto industry is rising up to the challenge by delivering new solutions to their consumers. We know that the consumer demand for connected automotive or connected cars has gone up significantly. The connected vehicle shipments will go from 52 million cars to 78 million cars in the next 3 years. And all these cars are being designed today. So the technology that's going into the cars is being designed and put into the solutions today. Technologies like cloud, obviously 5G, edge computing, computer vision, AI, and machine learning is fueling all of this transformation in the automotive industry. And this industry is undergoing a transformation unlike anything it has faced in the past. And so we're all sort of experiencing this as we're both technologists as well as consumers in this market. There's also a shift in consumer mindset. Consumers want experiences. They want personalized interactions. They have expectations that their digital lives follow them wherever they go. And so for the auto industry, this convergence of all of these factors is unlike anything that they've experienced in the past. So when we talk about connected car, what does it actually mean? Right? You may think to yourself, like, well, there's lots of different things when it comes to the technology of creating connected car or connected auto solutions. We do need to think about software solutions, software systems in the car that's collecting real-time data from the sensors, from the cameras, from lidars, and other sensors and other detectors in the car to make real-time decisions. There's also a need to bring all of that data that's being collected in the car into the cloud. And as you heard Adam say this morning, there's terabytes and terabytes of data being produced in the car every hour. So how do you bring all of that data to the cloud, and how do you make those decisions? There's also need to make some of the decisions within the car because of the latency requirements. So we'll talk a little bit about architectures that support that. There's also need to bring the data to some sort of a backend platform securely, first of all, where all of this data can enable services that are going to be needed both by the auto manufacturers and the auto OEMs, as well as the consumers. And then you need a system to perform real-time health checks on the car's operation, provide feedback loop on how the car is doing, about various critical components in the car. And then finally, if you deploy a fleet of connected cars, there's a whole other set of use cases and solutions that are needed to be able to perform fleet management, over-the-air updates, and ensure that there is a central system to do lifecycle management of the car. So there's a lot of different things and a lot of different components of the architecture that need to come together to support a connected car solution. But the possibility by collecting all of this data is endless. There's so many dimensions of how different types of solutions can be produced and provided. There are use cases, as we've all experienced in the entertainment industry. There are use cases from productivity standpoint, and there are use cases from digital e-commerce and just business-to-business type of use cases within the auto industry. When we talk about connected automotive, it means different things to different people. For OEMs, it is a host of new services to reduce things like warranty cost, replacement costs for parts, and things like that. There's use cases for managed service providers to be able to deploy new and innovative experiences and services to drive productivity and improve customer experiences. And there's also use cases in commercial fleet. So there's lots and lots of different use cases, but the underlying critical component is the data, right? Data is the key enabler. How that data is fueling innovation for the customers, how that data is fueling innovation for the ecosystem, and how that data is fueling innovation for internal insights for the car or the auto OEMs. And this creates tremendous business opportunity in the market across the board. But it's not very easy to do. What makes this hard? Well, first of all, communication is expensive. You can't really send or upload all of the data to the cloud. Also, instrumenting the physical world takes time. So how do we decide what data is important to collect and where those decisions need to get made? There's also security and privacy concerns. So when we're collecting all of this data at millisecond speed and bringing all of that data into the cloud, how do we do that securely? What sort of protocols we need to be supporting? And then deciding what computation to do on the edge, what computation to do in the cloud, and how to do that securely, both in the cloud and then within the car or at the edge. And then the next level of challenges come with organizational challenges. This is really hard for a lot of companies to do. Managing huge volumes of data is a whole new ballgame. So how do you collect all of that data? How do you build solutions on top of that data? And more importantly, how your team's performance is measured on the basis of data. It's just a new world, but also a very scary one too for many organizations. And then many organizations are also not set up to harness the returns from all of the insights and enabling this new paradigm for the consumer. So there's lots of different challenges, but surely and definitely the auto industry is moving in this direction. So with that, I'm going to turn this over to Michael to talk about what AWS solutions exist for automotive.
Thank you, Ritu. Hi, everyone. My name is Michael Garcia. I'm a principal product solution architect at Amazon. I've been working at AWS for 9 years. Most of my background is working and launching the IoT services that exist today. And now I'm focused on BlackBerry IVY. So in this section, we're going to talk about the technological impact that exists when you develop a digital product, because as Ritu mentioned, that's what the vehicles are becoming. And then we'll also talk about the software architecture that you have to put in place to make possible that vision of software-defined vehicle. So one of the things that is different that we have seen in the IoT world when you develop a digital product is that you have 3 teams that really have to work hand in hand. And organizationally, those 3 teams might be in different silos, but you really want to make sure that there's connective tissues between them and incentives for them to work together. The first one is the hardware team, so the people developing the hardware components for the vehicle and the car itself. The second one is the software team, IT teams. So you've seen that a lot of automakers have started to hire a lot of software talents to make sure that they can build software in the vehicle, but also the cloud vehicle connected backend that the vehicle is connected to. And the third team is the product team owning like the delivering of the feature for customers. And here customers are pretty broad terms. It could be consumers if we're talking about retail cars, but it could also be companies if we're talking about fleet use cases, for example. And so the value when you develop a digital product, the value goes beyond just having a digital product and services delivered by the digital product. For example, now with the digital product, you can collect a lot of telemetry data coming from the vehicle. And that's very useful in the rest of the company for the engineering teams that are producing, working on the battery management system, for example, understand better how the components of the vehicle, the hardware components are behaving, what is the performance of those. Another example is in the supply chain. Now with a digital product, you can track and trace where the product is. So for example, you can track and trace a vehicle once it's out of the manufacturing line and makes its way to be delivered to a dealership, for example. So that means better visibility over the fulfillment of orders and the ability to optimize those in the future. Another example in manufacturing is that with a software product, you can extend the quality control checks that are already in place in factories today. With the software, you can test some of the hardware, but also the other software features that are in the vehicle. And by doing so, you can prevent the operation of lemon cars. And last but not least, sales and marketing. You might have seen that more and more people are buying cars online, and then they're delivered to their driveway. So there's an opportunity there to specialize the software at delivery. For example, loading the profile of the buyer to greet them with a personalized message, but also buying the software and customizing that software package for the vehicle. So now we're going to zoom in a little bit onto the hardware. And just to level set here with the audience, we're going to talk about the hardware in the vehicle. So most of you might be familiar already with traditional vehicle architectures here, where there's a lot of ECUs in the vehicle that are siloed. And you might know that the industry has already worked its way towards consolidation of ECU by domain, so powertrain, body, chassis, and have added connectivity. So it could be in a limited capacity today. But in the future, everyone is geared towards a high compute platform in the vehicle and a lot of connectivity options. You've seen Adam talking this morning about 5G. There's also satellite connectivity that might exist if you're going into remote places and you need to manage all of that. As you can see, it's a journey that spans years, even decades. So when you have this trio, remember, of those three teams, the hardware, the software, and the products, one thing to take into account is that the refresh cycle are different. For example, for the hardware, you're looking at a refresh of every 2 or 3 years. And very similarly to the smartphone you have in your pocket. You buy the hardware, which is the phone, and then you change it after 1 year, 2 years, 3 years or more. But the software that is in your phone is updated at a much quicker pace. And so knowing that, we can design really a software architecture to make sure that it can take advantage of the hardware that is available, but remain flexible as well to be able to evolve at the pace of the hardware in the future. So now I'm going to talk about what would be the software architecture for a software-defined vehicle, putting those principles to use. The first thing is that you will have the hardware of the vehicle at the bottom. And then the first layer is the signal abstraction layer. So the ability basically to turn any sensor and actuator into the vehicle into an API to consume data from the vehicle signals, but also be able to write to the actuators. And normalizing some of the data to expose it to compute. And so we also have a compute abstraction module, which mission is going to be to run the compute workload. And in vehicles, there's many different levels of safety that are involved. So the implementation of the compute might take different form to conform with the different safety. So for example, it can be native processes all the way up to the use of containers. And as you might know, running containers, you can do that multiple ways. If you take the example of what's available on the cloud, with Fargate, it's very serverless. You don't see any of the underlying hardware. But you could also run different orchestrator, Kubernetes, like EKS. And so this module will, make it easy to deploy workload to the vehicle. Next up is machine learning. There are a couple of optimization that have to be done, making sure that if the vehicle has GPU, you can make use of those, compile your machine learning model so it's accelerated, but also pooling resources, so instantiating one machine learning model that can be used by multiple workloads to save on resources. And there's also optimization to the tool chain here and for developers to help, for example, gather the feedback on the prediction that you've made and send that to the cloud to measure the drift of your model and have retraining. Looking further ahead into the future, it's in that module that you could handle things like federated learnings, for example. Then you have operations. This one is pretty traditional in software architecture, making sure you can get the log of the systems, but also metrics on the performance, on how the components are doing, and enable debugging. Personal assistant, to have a layer of abstraction integrating with multiple personal assistants in the market, such as Amazon Alexa. Vehicle connectivity, again, to handle all the different types of connectivity. So this will go from Bluetooth, Wi-Fi, if you're in the home, to 5G in urban environment, satellite in remote environment. How do you make sure that you give the best connectivity option to a workload? What are the latency requirements of that workload? That modules will handle that arbitration. Also, it will enable you to control your cost, because maybe, if you have Wi-Fi accessible, it's going to be cheaper to use that than the 5G that is also accessible, and make it seamless for the application. Security, integration with hardware security modules to hold the private keys of certificate to provision the identity of the vehicle. And also, of course, security, it's job zero at AWS, so it goes across the board, really. And then we have the data communications, which is the gateway to the cloud and to the connected backend. So this is where we have telemetry, exchange of information, also command and control. And Henrik has a few examples of what command and control would look like. And then the next three are counterparts, mainly of what exists in the vehicle. And then analytics. Analytics is really important. That's where you will have your databases, data warehouse, lakehouse, data lake as well, and make use of the data for the rest of the company, but also sharing that data to other parties outside of the company, so you can look at things like monetization of the data. Pipeline will encompass building the different type of software that exists in the vehicle. There's going to be a lot of different types here to handle, but also keeping track with the graph database, for example, of the software components that are deployed to this specific vehicle. Which version are there of those different components? Tools will be extremely important. That's where it all comes together. So for example, if I'm a data scientist, I want to create a new machine learning model, I can access a unified data catalog of the vehicle, and then I see that maybe the parameters that I want is not available in the data lake because it exists, but it's not being collected at the moment. Well, the right tooling can empower me just to make that request, and then software can be deployed through the pipeline to the vehicle, so that then the data communication and the compute abstraction now is recording, getting that data from the vehicle, sending it to the cloud, and then I see it appear in my data lake. And finally, integrations, as we mentioned, with the web mobile application, but also manufacturing with ERP system or the rest of the supply chain. And again, security all the way. So in this session, as you see, the scope is very broad for a software-defined vehicle, and it's very deep as well, so we're very aware of that. This session is really focused more on the IoT services, so we'll talk more about the data communications. And Henrik, in a few minutes, will give you, very good overview of using AWS IoT Core and going into more details there. So zooming onto the vehicle here, you can see on the left side the use of Ivy. So Ivy is a product that is co-developed by AWS and BlackBerry. And for the purpose of this session, you can see it as a way to get access to vehicle signals, process them with or without machine learning, and then create an insight out of that, like the result of the processing, basically. There's going to be a Chalk Talk dedicated to Ivy tomorrow, AUT 307, if you are curious and want to learn more. And otherwise, I invite you also to go online to learn more about it. So now let's say that we have useful information, and that has to make its way out to the cloud. There's a few different routes. The first one is just integrating with a telemetry solution that might already exist. As you've seen on the hardware diagram, it's a journey that will take years. The software architecture is the same thing, and OEMs, automakers are at different places. So some already have some of those modules. So that's why it's an integration here with something that already exists. Could be also using the AWS SDK. They're open source, and they already include some of the mechanism that you would have otherwise to code yourself. Like retry logic with exponential backoff. They're updated as well by the AWS teams. So really it's there to give you a leg up in the development, but their use is optional. And then the option that was, that was launched today is AWS IoT Fleetwise. So again, a way to capture vehicle signals from the vehicle and upload that to the cloud. And so on the cloud side now, you have a different couple options to handle your data communications. The first one is kind of do it yourself, on top of EC2. You could create your own broker. Of course, in this approach, you have to manage the high availability, high scalability yourself, the security, the updates. So it's a lot of work operationally. You could deploy open source broker that exists out there on top of EC2. You could also look at other services that we have that are a bit more managed. You would still have to handle the scalability still in that configuration. So for those who want to go fast or wants to have a service that handles for you the scalability, the availability, the security, then AWS IoT Core is the right choice there, and supports multiple transport protocol, what is usually used in those architecture, MQTT, HTTP, and WebSockets. In addition, now, if you want to go further into the management, AWS IoT Fleetwise will enable you to extract data from the vehicle by configuration of the agents. So it's adding value there. And then just to mention a couple of other services, if you have to handle different types of data that telemetry and control, if you have to handle sound or video, for example, video, you might want to take a look at Amazon Kinesis video streams to do that. And the last piece is the integration, again, there to integrate with web, mobile application, and the rest of the backend as well. And so now I want to do a little bit of a zoom on Ivy and AWS IoT Fleetwise and take a use case to do so to show you how they could work together. So here in our vehicle, we have the AWS IoT Fleetwise agent already deployed. It can collect sensor data, then send that to the cloud. One thing you can imagine in combining Ivy and AWS IoT Fleetwise is that if you wanted to do scene detection, for example. So let's say you're interested in detecting when there is a stop sign on the road because you're building a map. So you could have Ivy doing all the computer vision on the frames of the camera here to make that detection, and then send that insights to AWS IoT Fleetwise so it can make its way to the cloud. So that's one way they're complementary. That's not all. You could also use IVY as a trigger to tell AWS IoT Fleetwise, now start the collection of data, because there's something that I've detected on the road, for example. And the last one is using one of the Fleetwise capabilities. It's just to sample the data coming from vehicles. So if you have a fleet of vehicles, let's say they're all in the same location on the highway, maybe you don't want to have all those messages going to the cloud. You can use Fleetwise to kind of sample only a few cars, giving you that information if they're in the same location, for example. The rest of the architecture here is just really to handle that use case. So nothing very specific here. You have the use of machine learning, operation. It could be other services here. It's just an example. And then some OTA capabilities that can be done a different way as well. And so what you see here is that we're releasing more and more, and you might have heard that from Adam this morning, more and more services that are tailored to industry vertical. And so IVY and AWS IoT Fleetwise, they're really example of that. As you see, we're trying to help into that map of software-defined vehicle. You've seen that there's a lot of modules there, so you can expect from us, further help in the years to come, and also additional services that will be tailored to the automotive industry. And with that, I'm going to hand it off to Henrik. Thank you.
All right, thank you, Michael. My name is Henrik Stromberg. I come from a company called Wireless Car. Wireless Car is making back-end solutions for connected vehicles. And we're based in Gothenburg in Sweden with 100% automotive focus. Although the connected vehicles is pretty new, we've been doing this since 1999. So we have almost, or more than 8 million connected vehicles in our systems. And we're located worldwide in more than 85 markets. So we have a lot of customers. We have Volvo Cars, Mercedes-Benz, Subaru, Jaguar, Land Rover, and so on. But I'm here to talk about what we do with Volkswagen Group. And that's the customer I've been working with for a couple of years now. And we're going to look into a little bit what we're doing with them. So Volkswagen Group, that's a huge company. They have 662,000 employees. In 2020, was a bit of a downturn for the automotive industry, but they still produce 9.2 million vehicles. And they not only produce Volkswagen vehicles, they have brands like Audi, Skoda, Seat, Lamborghini, Bugatti, Bentley, and a few others. So it's really, really big. It's based in Wolfsburg in Germany, of course, and then, but they have 118 production sites worldwide. So really, really, really big. So what are we doing with Volkswagen Wireless Car? Well, the business goals and the challenges that we have is that we were asked to provide a back-end solution for the connected vehicles or connected services for the vehicles that are based on their latest platform. And their latest platform is the electrical platform. They're going almost all in on electrical vehicles. It's called MEB. I don't know if you know, but they have vehicles such as the ID3, ID4. Excuse me. Audi has the Q4 e-tron. Skoda has the Enyaq. And there are many, many more models to come also in the coming years. And there's more already. When you're developing a back-end or connected solution for the vehicle, security, like Michael mentioned, is of the utmost important. Security in the vehicle, security in the communication to the cloud, security in the cloud, data protection, that's really, really important. And also, a breach of security in a vehicle could potentially be far more serious than other areas. Like, if the volume of the radio turns up to max, that could be really, really dangerous if it's done suddenly. Also, another challenge or something you have to consider is the variability. And when I say variability, I mean variability in number of vehicles over the years. There's many, many millions of vehicles that are going to go on this platform. Variability in the number of services and the scope that these services will actually have during the lifetime of a vehicle. Variability over the the day in traffic patterns. So that's something that your architecture and your way of working needs to be able to handle. And lastly, also requirements. Developing a car, it takes 3-4 years to develop a new car, and you develop the software alongside the hardware and the wheels and the steering wheel and the roof and all that. But the requirements in the beginning of such a cycle is going to be different than what you end up in the end. So you need to be able to handle this changing requirements along that way, kind of in an agile way, even though developing a car is pretty much waterfall in other aspects. So that's something that we need to handle when we do this. So you mentioned a little bit about what connected services are. I'll give you some examples of what we have. The ones that are end user visible. We have about 50 different services in this backend for Volkswagen, but these are the ones, or some of the ones that you can see as an end user. EV services, electrical vehicle services. These are some screenshots for the app. You can view the range of the car, the state of charge, the temperature in the car, so basically a remote view of your vehicle. You can control the vehicle a little bit. If you want to start the charging at a different point in time than when you actually plug in the cable, you can do that by controlling it, setting it on a schedule. Or my personal favorite now when it gets cold outside, well, not here in Vegas, but in Sweden where I'm from, we're having a foot of snow actually right now. Preheat the car. When you get out in the morning going to work, it's nice and cozy. That's a really killer thing. But other things like status of your vehicle, check if it's locked, did I lock it when you left it, find it if you forgot where it's parked, but also get dashboard information about warning lights in the dashboard. You get that to your app. Or things like roadside assistance, if you have a breakdown and you call the call center and they get data about your vehicle, what's wrong, where it is, and they can do the appropriate things that need to be done. So that's just some of them, but there's plenty more, of course. So how do we do this? Of course, we use AWS. Like I mentioned, we have about 50-ish different types of services, so we have divided those into a microservices architecture. What's really important for us is to try to keep these services separated. Working in a service isolation manner. We want to have as little dependencies and as little impacts between these services in runtime. Because if there's a failure in one, we don't want the other service to be impacted. We're using a lot of asynchronous and event-driven patterns to be able to handle the variability in traffic load, really. You'll see an example of that later on. The picture to your right here is a typical service setup. It's not entirely like this for all the services, but it's a blueprint, really. We're going pretty much all serverless, and the core here in the communication with the vehicle is the IoT core. Most of the communication is done over MQTT, and we're having hundreds of thousands of cars already. We've been live for a little more than a year. But foreseeing, of course, millions of cars being connected. And these cars are connected 24/7, pretty much. They're communicating over MQTT, as I said, protobuf as the payload. Protobuf is a binary format, which is very small, makes the messages small, but it's also extensible into the future. You can add things to that protocol without impacting the software in the vehicle. And that is really important because over time, your services are going to evolve during these 10 and 15 years, and you want to maintain as few versions of the software in the back end, or a few versions of the payload format for easier lifecycle management, really. Once the messages get into the back end, the main business engine is run by AWS Lambdas, using integrations like SQS, SNS, Kinesis, Persistence, and Dynamos. And then these services can expose that data to apps or backends for apps, where we have the API gateways, mostly over standard protocols like HTTP with JSON payload. So this is a very typical blueprint of the services that we have. And it's built for scale, really. Scale and variability. So I'm going to go through a couple of flows that we have on a pretty high level, but still. That is necessary in order to achieve all this. First of all, we need to be able to register a car, add a car. And that is done by cars sending a certificate signing request, a CSR, to the backend, saying, hey, I want to be part of this ecosystem. And we validate that CSR and sign it to create a certificate. As a result of that, that certificate goes on to the IoT core to create a thing. So this certificate identifies this car individually. We create, alongside with this, what we call an external ID. And an external ID is also being part of the policy that sets up the MQTT topics. So that we have topic structures for both published and subscribed messages. And this means that each vehicle has its own set of topics so that they can communicate with vehicles individually. And this is really important, of course. Once that is done, the certificate is returned to the vehicle, and then the vehicle can use that to connect to the IoT core, which then enables it to basically receive and publish messages and information to the backend. So once that is done, we want to send the state of charge for the vehicle. I'm loading my car. I want to see in my app what's the state of charge. The vehicle is connected to the IoT core, sending an MQTT message to the backend. What we have then first is kind of not a simple Lambda, but it's a routing engine, taking that message, looking at it, and looking at who's the target service for this message. And then, as I mentioned, these services are divided individually, and typically that message is forwarded to an SQS, which is picked up on a Lambda in the target service, which then does whatever it's supposed to do, store it, notify some subscribers, or whatever. Pretty straightforward. Going the other way around, though, producing service to the right, I want to send something. We want to keep the producing service unaware of the communication protocols that we need to do with the vehicles if that is to change. So it's sending its request through an API gateway to this routing function that we have, which looks at the message and then figures out which topic am I going to send it to. Also figuring out which vehicle, mapping it to the external ID, as I mentioned earlier, ending up on the IoT core, which then is responsible for forwarding that to the vehicle. So, yeah, very typical flow. During this journey, when we developed this, we also learned a couple of things, a couple of lessons learned here. I don't know if you remember, just 2 slides back, the uplink flow here from the vehicle to the backend. We used to have it like this, an SQS consuming message or getting the messages off of the IoT core and then invoking a Lambda from there in order to be able to batch process messages. Then you can take 10 at a time, be a bit more efficient, save some money. However, the world is not really ideal. Usually, when you have this setup, there's a constant stream of messages from the vehicles. So the backend is scaled appropriately to handle these messages. But even mobile network operators, MNOs, they have outages. So when we got an outage, the stream of messages, they stop coming. And of course, the backend adapts to that, scales down. But then what happens when the vehicles then regain that connection, they have piled up a lot of messages, and they're all flushed. Hundreds of thousands of vehicles sending many messages at once to the IoT core, no problem. Then we ran into a challenge about scalability or speed of scalability, really elasticity, when the Lambda was going off of the SQS. And when you couple that with some vehicle behavior, resending messages when it didn't get a response quickly enough, then what happened was that the SQS was just getting more and more and more and more messages. And they were not really consumed quickly enough for that case. So we changed the architecture into this. We removed that SQS and had the Lambda being invoked directly from IoT core, which scales quicker, little bit less efficient from a cost perspective, but it does what it's supposed to do. And we know that that architecture will probably have to change going forward, maybe looking into Kinesis. And so I was really thrilled this morning when I heard this serverless Kinesis thing. That was a good thing. Going forward, this one is something that is really good for us, really to reduce runtime dependencies. And what I mean with that is be kind, really be nice. When you're running serverless or in the cloud, you basically have all the resources that you need whenever you need it. And if you have a dependency or using a downstream service, you can really just overload them really, really easily. So you need to be nice, and a couple of ways of doing that is to keep local copies of the mostly used data. If you don't really need to go somewhere else to get something, keep a local copy and maybe even caches of some things. And one thing was almost a funny story now in hindsight. Before we went live during development, we were running some game days, load tests jointly for all the services in the backend. Represented here by S1, S2, and S3, different services. They were getting a lot of requests in a load test. So what happens then is that the Lambda starts scaling up, new invocations. All of these Lambdas, they needed a token from the identity provider. So they all went there. And when you scale up, all these, they were just drowning that IDP. So the IDP was overloaded, stopped responding. These Lambdas were sitting there waiting for a response. Requests were still coming in, more concurrency of the Lambdas were starting up. So it ended up, we brought down the IDP, we exhausted all the resources in the account, and basically the whole thing came to a stop. So, okay, what we learned was keep a local copy of the mostly used data. Download that token and keep it for that service locally, even if you have serverless, which is supposed to be stateless. So you pick it up from a local database instead of going to the IDP. And then instead of getting thousands of requests to the IDP, they got like 30, 40. So a lot easier. So this is one way of reducing those dependencies I was talking about earlier. And of course, fail fast. Everybody says that. If you know that your service or something that you're contacting usually responds in 200 milliseconds, don't stick around for 30 seconds. It's not going to be worth it. So that has really served us well in trying to reduce those runtime dependencies. Third lesson, not too late, but this is something that is also promoted by AWS when it comes to how you organize your accounts. Have service accounts. Like I mentioned, we have about 50 services. And in the beginning, or if you don't split them into different accounts, you're going to have all these services competing for the resources in the accounts. When you run serverless, you have limits on the account level, which is really a good thing, because otherwise you could get broke really quickly. But all these services are not used equally. So if you have here two different services, you have the orange service, you have the purple service, and the orange service, if it's used a lot, it could really exhaust the resources in the account from the purple service, basically becoming a noisy neighbor. And that's what you want to avoid. You want to guarantee that you have the resources that you want when you need it, but you still don't want to impact other services. So by doing that, by putting those services into different service accounts, is really, really good. Now, looking ahead a little bit with the journey we have done, but also start off by looking back. I must say, I think that serverless has served us really well. We have been able to focus on the business logic to add user value instead of focusing on managing databases or queues or load balancing or failovers. That's all taken care of. So from that perspective, I think it works really, really well. Going forward, though, in this industry, I would say a lot is about scalability and scaling. There's new services, new vehicles, increased demand for traffic and data, so your backend really needs to scale. Coupling that also with cost management. Just scaling is, well, not easy, but it's you got to do it efficiently or cost efficiently. And that means that the architecture might have to change along the way, because some architecture or one architecture may be cheaper today, but as the scaling grows, as it takes more traffic, you may need to transition into another one to keep the optimal cost level. So that's something that's constantly overlooked when doing these backend solutions. And the third one, really, service efficiency. And I'm not talking about the code of the services that you have, but really how they actually work with other services. Do I need to make that extra request over here? Can I scale down a little bit in order to be able to scale the way you want or handle the traffic from the vehicles that you want? Like you said, data transfer is expensive. You want to keep it to a minimum, but not less than you actually want or need. So that balance, the efficiency, service efficiency in that balance. All right, thank you.
So thank you for the time. Today we do have some time for some questions. So if folks have questions, we can take them now.
I have a question about cost. Where do you see the cost landing? Like at the car manufacturer, the fleet, consumer, and if it's variable, I mean, just thinking through that, how would it affect the consumer?
So I can repeat the question. I think the question is about the cost. Like, where does the cost land? Does the cost land with the consumer, with the fleet, with the car manufacturer, and so on? Henrik, do you have an opinion on that?
I think it's going to vary a bit depending on what kind of services that you actually offer. Some are definitely going to be taken by the car manufacturer because they are the ones who are interested in that data. Whereas other services is something that you sell to your end user. And then you can incur that cost to them. So I think it's going to be a variance here.
Thank you.
There's a question in the back.
Yeah, I have a question. When we talk about failure with communication, it could have to do with SIM cards and whether it's an accident or whether it's something that's an emergency, collecting data like that can get lost. Technology which exists today called software-defined networking, where you can combine the best of two. You may have one lousy network goes down and the other network switch over automatically. Is that something that this industry is looking at for those kinds of use cases? So safety, an accident, you want to collect all that data right away, as well as service just goes down instead of an outage, but other carrier may not have an outage. You have two SIM cards or two connectivities in each car.
Do you want to repeat the question first and then?
Yeah, so I think your question was around connectivity, and so in the if there's an accident that happens or like an event like that, how can you leverage different connectivity options, and also how do you make sure the data is not lost if you're keeping sending it? Is that main? Yeah. So yeah, you're absolutely right. I think like when we talked about it, it was like sending data continuously. But you can, the first answer is that you could also have some of that data keep being local. If you don't need to send it straight away, that's why we have compute elements on the vehicle, like IV, for example. So you could detect a collision, and then you could keep a buffer locally that just like writes over. And then if you detect like the right even, you could tell the buffer, okay, now that one, like that's the snapshot that will keep there. Now, if you also want to send that to the cloud with that collision, then you can do that through different connectivity options. I think you also mentioned like different SIM cards and things like that. So absolutely, like you would look at what's available, again, with the latency requirement that you have for that. And I think it would be very important, and depending on the use case, to really size well like the snapshot that you would take for like a collision, for example, like what's important to you. And then you can also make sure that, yeah, you have different connectivity options to do that. Yeah, absolutely. And so just to repeat for the other people in the other rooms that cannot hear you, yeah, you would have also like different SIM cards there, and like you mentioned, luxury cars. Also, they're more capable, so you can also augment like the availability of the connectivity options with other cards.
There's a
There's one
question here.
Oh, sorry.
Diagram of the car sending information was first went to that Lambda function, which in turn send it somewhere else, right? So to avoid the batch processing, and then you had another where the communication was going the other way, and I wasn't sure how fast the messages were. But if the car was sending frequent messages, could it maybe just pick up, check to see if there is anything, waiting in a message box, like you have like
Q.
yeah, like a queue,
Yeah.
right? As opposed to, because it looked like going back the other way was supposed to. Maybe the car, when it sent messages, could have just checked to see if there was something waiting in the mailbox. If it's sending a lot of messages, would that be more? Because you were concerned about efficiency.
Yeah.
Maybe that doesn't make sense.
Did I get your question right? If it would be more having a buffer in the car of messages, is that what you said?
Well, so here, what we've got is all the messages are coming in frequently, but when we're sending back messages, are we sending back messages as frequently? Like, does that happen a lot at the same scale?
So the question was if the uplink from the vehicle and downlink messages are as frequent. No, I would say that the car usually, my experience is that the car usually sends more messages than it receives.
Okay, so maybe if it just checked if there's something waiting rather than pushing, or is that what's actually happening here?
I would say they're different things. There's not really request and response in general. So the vehicles kind of hand off information which you want to process and maybe forward to other interested parties. And then as a result of that, there may be things happening, and then there's a message going back, but not far from always. So.
Yes.
So beyond the access control from a security perspective, do you implement other security protocols?
At which level of the security protocols?
So you illustrate this, the certificate, how the certificate is required, right, in order to provide access control.
Right.
Right, but there is confidentiality of information, there is availability of service, there are other security attributes, and the question is, are these somehow implemented in the solution?
So the question was if there are other security attributes than just the authentication with the certificates. Yeah, of course, there's also payload encryption within that. And then everything is encrypted in the back end. There's access control from a privacy perspective, which is really, really, really important in this industry because there can be some really sensitive data like GPS positions that can be used in a not so nice way. So you really have to protect that data both in the vehicle and in the back end. There are actually, it's quite common that you actually separate the different ECUs you were talking about, not knowing what the other ECU is actually doing. So having an in-vehicle encryption of data because you need to pass through a gateway or something just to make sure if that ECU is compromised, you don't leak that data. So there are a number of levels, definitely.
Yeah, and then I would add that even on the service side, right, there has to be security implemented in all of those services. So what access to the data each of those services have, and then there's also, like, if you have a fleet of cars in different countries and things like that, like what data you have access to or what data you don't have access to. So then, security in the vehicle, security during the communication of that data, then in the cloud, and then as the services are being invoked, what access to the data these services have. I think security has to be implemented at all those levels.
And just to add a little bit, the question about privacy and GDPR is taken really, really seriously.
Yeah. Other questions? There's a question here.
Yeah, so your choice to generate one set of topics for the vehicle, I assume like to go to the VIN number, is quite interesting, opposed to using like some kind of
Not yet. I mean, these topics it's a structure, which is one hard-coded part. Sorry, question was if there's difficulties in managing all the topics that we see. Not yet. The IoT Core is able to handle these topics quite well, I would say. I think they're more logical in that architecture, not sure. But what we're doing, we're having a certain set of topic structure in the beginning, and then you can add on for the specific services. So, no, not really. Anything else? All right.
There's one more question here.
Just a comment on the last. I think what we have seen is that there is a limit on the number of topics that you can connect the device to.
Yeah, it is. And, well, basically, there's a limit to the number of topics a subscription you can have per subscription or connected to it. So, but if you can do it, if it's okay for the client, you can do a wildcard subscription. So even if you have 200 topics per client, if you do a wildcard subscription, it counts as one, which is quite handy.
Great. Thank you, everyone, for your time. Hopefully, you found the session useful, and you could see how IoT Core, BlackBerry IVY, and IoT FleetWise, as well as other AWS services, help to pull the connected automotive solution together. We're going to stick around for a few minutes if you have any more questions. Please don't forget to fill out the survey for the session. And again, thank you for the time today.
Thank you, everybody.
Thank you.